Hi, this is Physics 503 Nuclear Physics, and in this lesson, we're going to discuss the overview of nuclear reactors and research reactor technology. In the first part of this lesson, we're going to discuss the main drivers of your nuclear power technology, and in the last part, we're going to discuss some of the main issues that we are considering, especially in constructing a nuclear power plant in our country. So let's start with the basic question of what is a nuclear reactor. Nuclear reactors are devices that produce and maintain a steady flow of neutrons generated by a fission of a heavy nuclei. So the image on the right is an example of what a nuclear reactor looks like. So the working principle behind your nuclear reactors is this process which is called your nuclear fission. Nuclear fission occurs when a heavy nucleus, such as your uranium-235, splits into smaller nuclei. Like say for example, into krypton-92 and barium-142. This is initiated when a heavy nucleus captures your thermal neutrons. Later you'll see why it is important that you have your thermal neutrons. The absorption of the neutron creates a nucleus that is unstable. Like say for example, for this case, you have your uranium-236, and since this is unstable, it can change to a lower energy configuration by splitting into two smaller nuclei. This is explained by your liquid drop model. Nuclear fission was first observed in 1938 by Otto Hahn, a German chemist, and Fritz Strassmann, a German physicist, following some basic studies by Fermi. This was observed again in 1938 when the Germans, led by Adolf Hitler, was busy convincing the world of the superiority of the Germans. And this was during the World War II. Shortly thereafter, Lee Smitner and her nephew Otto Frisch explained what had happened. And they found that after bombarding uranium with neutrons, Hahn and Strassmann discovered among the reaction products two medium mass elements, barium and lanthanum. And after absorbing a neutron, the uranium nucleus had split into two nearly equal fragments plus several neutrons. Again, this is explained by the liquid drop model. Measurements showed that approximately 200 mega electron volt of energy was released in each fission event, and this fact was to affect the course of the history. So after this discovery, the German Nazis or the German government or the Nazi government actually started research about this one. As you can see, it can produce 200 mega electron volt of energy, which can actually be used in the war. And then Albert Einstein found out about this and wrote a letter to President Roosevelt about the dangers of nuclear fission. And from that started the Manhattan Project, which made the first nuclear bomb, which was first dropped in Hiroshima and Nagasaki, which then ended the World War II. The fission of uranium-235 by thermal neutrons can be represented by the reaction given below. What you have here is a stray neutron that hits uranium-235 or is absorbed by uranium-235, which then forms an unstable uranium-236. And since this is an intermediate excited state or unstable state, this lasts for approximately only 10 to the negative 12 seconds only, before splitting into your medium mass nuclei X and Y, which are what you call your fission fragments, and also produce other extra neutrons in the process. Fission also results in the production of several neutrons, typically 2 or 3, and on the average, approximately 2.5 neutrons are released per event. As you have seen in the previous slide on the representation of the process of nuclear fission, there are extra neutrons that are produced in the fission process. For example, you have a typical fission reaction for uranium given below. You have a stray neutron, or just one neutron that hits a uranium-235 nucleus. And since this is absorbed, it produces again an unstable uranium-236, which then splits into your barium-141 and krypton-92. And this process produces around 3 neutrons. And As you can see here in the figure, this just started with one neutron hitting your uranium-235, but this other neutrons that were created under process actually hits other neutrons around your around your chamber, for example, which then triggers a chain reaction. And this chain reaction in your nuclear fission is what creates the power, which is 200 times the power of the initiating neutron, which is this one here, which creates very large or massive power, which can be used in your nuclear reactors or even also in nuclear bombs. We have two types of nuclear reactors. The first one is your research reactors, which generates neutrons for the use of research in medicine, in agriculture, and etc. The second type is your power reactors, which generates electricity. And for this lesson, we are going to focus on your power reactors, the one that uh, is more commonly known as your uh, nuclear power reactors, or your NPP or NPR. But let's define first what research reactor is. So typically on the image is an example of a research reactor, which is simple in design and construction. We actually have a research reactor in the Philippines, and uh, this is located in the Philippine Nuclear Research Institute. Okay, and you can view it in the internet how it looks like. But typically it just looks like an egg outside, but you have a research reactor inside of it. It operates at lower temperature and pressure, and it needs a smaller core, which means it needs less fuel. But this also produces less fission products build up. And generally, higher enriched uranium, up to 20% uranium-235, is used in your research reactors. This has smaller exclusion boundary as compared to your power reactors, but has benefits from reflectors to reduce your neutron loss. And for your research reactor, water is used for cooling and moderation of your neutrons. As of July 6, 2018, we have around 840 research reactors that were built around the world, but only 225 of this one is operational and 57 are in permanent shutdown. 14 is in extended shutdown, including the PRR1, which is the Philippine Research Reactor in the Philippine Nuclear Research Institute. So we actually have a research reactor in the Philippines. It's again called your PRR1, but it's not in use. It's in extended shutdown. But there are plans to revive this one or to commission it again, which is called your Satur plan. And we're going to discuss more about the Satur plan in the next lessons. 10 are under construction, 13 are planned, and 66 under decommissioning, and 442 are decommissioned. Decommissioned meaning it's not anymore used and will not be used anymore. So as I've said, in this lesson, we are going to discuss more about your power reactors, and we'll have a brief overview of the nuclear power reactor technology. We are going to discuss the current global status of nuclear power, the perspective of nuclear power generation main drivers, and the overview and general components of nuclear power reactors. And we're going to discuss also the power reactor nuclear steam supply system and also the types of your power reactors. So what's a power reactor? A power reactor is also called an atomic furnace. So a power reactor is a nuclear reactor that produces and controls the release of energy from splitting the atoms of certain elements. Like say, for example, of course, your uranium-235. In a nuclear power reactor, the energy released is used as heat to make steam to generate electricity. So it's just actually the same as your fossil fuel plant or your coal power plant. So the energy release is used to boil water to make steam. And this steam here, generated from the boiling of the water, will be used to power up your turbine, And when this turbine is powered up, it will move your generator. And by electromagnetic induction, will create electricity powering up your cities or your homes. So from your nuclear energy, you produce your heat energy in the form of your steam. And the steam will, the kinetic energy of your steam will be used to move your turbine, which then is transformed into electrical energy via your generator. So it uses a lot of thermodynamics and electromagnetism in just producing your power in your nuclear reactor. But again, this is the same process with your fossil fuel or your coal power plants, which uses heat energy to form steam in order to drive your turbines. Let's discuss the different outputs in your power reactor. One is your thermal MWT or your megawatts thermal. This relates to the quantity and quality of the steam produced. And we also have your gross electrical megawatt electric, which is the power produced by the turbine and your generator. And then we also have your net electrical megawatt electric, which is the power sent out from the plant to the grid. What is actually important here is your net electrical or your net electrical megawatt electric, because this is the actual energy that we are going to use in powering up your neighborhood. So this is again the power sent out from the plant towards the grid. So you have your megawatts thermal, your gross electrical megawatt electric, and then your net electrical megawatt electric. Let's look at the overview of your nuclear energy around the world. So this is a map of the world of the nuclear industry performance in 2019. And we have around 442 nuclear reactors around the world, which is divided into 30 countries, and we have 53 under construction. But of course, we do not have one here in the Philippines. We do not have a nuclear power plant here. Most of the nuclear reactors are in France, which actually powers up 70% of their energy. So also we have increasing interest of using nuclear power plants in Asia, specifically in China and South Korea. This is the regional generation. There's an increase in generation in Africa, Asia, South America, and East Europe and Russia. And there's a strong growth in Asia, which saw nuclear generation rise by 17%. As I've said earlier, there is a strong increase of nuclear interests in Asia, specifically in China and South Korea. This one here is, this graph here is for Asia. And however, there is a decrease in interest from the West and the Central Europe. So most of the reactors now uh, are in France, and we have at least 56 number of reactors in the French nuclear reactors, which produces an output of around 382.4 terawatts per hour. These are the top 10 total operable reactors. 95 are in the United States of America and 56 are in France. And we have 48 in China, 33 in Japan, 38 in Russia, and we have 24 in South Korea, 19 in Canada, 15 in Ukraine, 15 in United Kingdom, and we have only 6 in Germany. Germany is actually an interesting country to study your nuclear reactors because, as you can see, it's a developed country. It's a first world country, but as you can see, they only have 6 operable nuclear reactors. There is this movement in Germany wherein they are planning to finally remove all these or stop using your nuclear reactors, which is in contrary to their claim that they wanted to uh, remove anything that any electricity generation which produces greenhouse gases. But as you can see, nuclear energy is actually a clean energy, but Germany is trying to get rid of it. But there's an uh, interesting issue here in Germany when it comes to your nuclear reactors. And this is actually because of the various incidents, like say for example your Chernobyl incident, and then of course also of the Fukushima incident. These are the top 10 reactors under construction, top 10 countries. You have 11 in China, 4 in South Korea, and 7 in India, 4 in Russia, 4 in UAE, 2 in UK, 2 in Japan, 2 in United States, 2 in Turkey, and 2 in Belarus. And as you can see, among the top 3 is found in Asia, which is in China and South Korea. So these are the breakdown of the reactors under construction. So for boiler water reactors in Asia, FNR 2, and a total of 37 reactors are under construction in Asia, and the rest are found in East Europe and Russia, North America, South America, and West Central Europe. Still no plans, of course, in the Philippines. And this is the world electricity production by source. As you can see, we still have 36.4% of our energy production, which is dependent on coal, 23.3 dependent on gas, and 15.6 dependent on hydro, 5.3 dependent on wind, and you have 10.4% dependent on nuclear. And you also have other sources such as geothermal, biomass, and other renewables. And only 2.7% of this is in solar energy. So why is nuclear energy so special? These are the main drivers of your nuclear energy that makes it so special. One is you have high power density. Second is you have supply reliability. And then, of course, in economics, an increase in fuel cost and your carbon emission cost and on your operational history and safety. So we're going to discuss this one by one. First, let's talk about your high power density. So what you see in the image is a nuclear fuel pellet, which is actually very small. And because of this one, you have a high power density, which you will see later why. And you have, let's talk about the energy produced by this fuel and the land footprint to produce this energy. So your uranium fuel pellet is just 9.11 millimeter in diameter, and it has a height of 11 millimeter. It is very small, but one pellet can actually produce 5% kilowatt per hour of energy, enough to power one town. So one uranium fuel pellet has as much energy as 17,000 cubic feet of natural gas, has an energy of 149 gallons of oil, and has an energy equal to 1 ton of coal, which is a lot. Okay. If you're going to compare your just one pellet of your uranium, compare it to 17,000 cubic feet of natural gas, 149 gallons of oil, 1 ton of coal is very uh, efficient as compared to the other sources of your energy. So the fuel that is mostly used is your uranium, which is a relatively common element in the crust of Earth, very much more than in the mantle. It is a metal approximately as common as tin and zinc, and it is a constituent of most rocks and even at the sea. Some typical concentrations are in parts per million. So again, uranium is a relatively ordinary element. You can find its trace in rocks, seawater, etc. However, the number of repeatable uranium reserves is not so many. The world's known uranium resources increased by at least 25% in the last decade due to increase in mineral exploration. The uranium resources are widely found in nature, unlike your petroleum or your coal, which can only be found in specific area. The value of uranium resources is dependent on their production cost, and at present, the present uranium price is on the downward trend. We have three naturally occurring isotopes and three artificial isotopes produced in your reactors. Natural uranium is constituted primarily of uranium-238 with 0.72% uranium-235 and a small amount of isotope 234. Three isotopes of uranium, uranium-236, 233, and 232, are also produced by reactors from uranium-235 and thorium. These are the natural and artificial isotopes, which are your alpha emitters. So again, your natural isotopes are uranium-234, uranium-235, and uranium-238. And your artificial are uranium-232, 233, and 236. So again, uranium, this is the fission and chain reaction for your uranium. We have already discussed this one earlier. The fission of uranium-235 atom produces two daughter elements, often but not always your krypton and barium, and it also produces a large amount of energy plus additional neutrons, creating a chain reaction. Your neutrons released from the splitting of one atom cause fission in additional atoms. So as you can see here, which creates the chain, and these atoms in turn release still more neutrons, leading to a growing chain reaction, releasing more energy in the process. These are the discovered reserves of uranium as of January 2017. So we have a lot of reserves in Australia, in Kazakhstan, and in Russia. We also have some in South Africa, in China, in Mongolia, and in India. So there, or as you can see, uranium is very much available in many areas, unlike your coal and your fossil fuels in your natural gases. These are the identified uranium sources among 15 countries that are either major uranium producers or have significant plans for the growth of the nuclear generating capacity. 50% of your uranium sources, of our uranium sources, are found in Australia, and we have 14% found in Kazakhstan, and the rest are spread out in the other parts of the globe. Of course, there may still be other areas which are still undiscovered, but as you can see, your uranium sources is um, spread out evenly across the globe, unlike again your fossil fuels or your natural gases. We have a uranium mine in Kazakhstan. So it's the largest uranium mining area in Kazakhstan in Akbastal mine. And you also have a mine in Karakau mine. We also have uranium mines in Chu Sarisu and Sirdarya uranium province. These are still found in Kazakhstan. So Kazakhstan is really a uranium mining province, as you can see. We also have uranium mines in Canada, mining at the MacArthur River in the Kamikos Cigar Lake. We also have uranium mines in Australia, the largest source of your uraniums around the world. This is the uranium price throughout the years. There was just a steady increase in the price uh, around 2005 to 2007, where at 2007 you have the highest price uh, of 354 US dollars per kilogram of uranium. But after 2007, there was already a downward trend in the price of your uranium up to um, 84.36 US dollars around on 2020. Okay, and the lowest price now is just around 66.14 US dollars per kilogram of uranium, which is the price last November 15 of 2020. So this is your uranium nuclear fuel cycle. It starts in your uranium mine, and then where you can get your uranium ore, and from that it goes to the milling plant, and then your your uranium concentrate, which is a yellow cake, will be refined and converted in your refining and conversion plant. And then from this start the process of your uranium hexafluoride, and then up to your uranium enrichment, up to the reconversion plant, uranium fuel fabrication, and it goes around until it's used in your power plant. And you also have your disposal facility, of course. Let's talk about the power density in terms of land footprint. Let's compare your wind, your solar, and then your nuclear. And as you can see, for your wind, you need 260 to 360 square miles for 1000 megawatts of energy. And for your solar, you need around 45 to 75 square miles for just 100 megawatts of electricity. But for your nuclear, you only need 1.3 square miles for 1000 megawatts of energy. This can be seen here in comparison. This is the square miles needed for your wind. Okay, this is for your solar, and then this is for your nuclear. Compared to the wind and the solar, um, your nuclear only takes a very small uh, area of land to produce 1000 megawatts of electricity. And if you can remember, your wind and then your solar are actually small sources of, or it can only produce small amounts of energy. That's why you need larger plants or larger areas for this one to produce 1000 megawatts of electricity. Just in comparison, you have here your Andasol 50 megawatt solar parabolic flue in Spain. So it really takes up a lot of space. And this is the Bangi wind farm in Ilocos, which can produce 30 megawatts of electricity. So it can produce 33 megawatts, but as you can see, your 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 wind farm can actually take up a lot of space. So as you can see here, it takes up mostly the shoreline of your ocean. Compare it with your power plants. Take for example for your Korea nuclear power plant. So this is just a very small area, but it can produce around 1,200 megawatts. If uh, the Bataan nuclear power plant was commissioned, it has a nameplate capacity of 621 megawatts. This is just a very small area compared to Bangi uh, wind farm, but this can produce a lot more energy than the one in Ilocos. Now let's talk about the next main driver of your nuclear energy, the supply reliability. Most demand of electricity is for continuous reliable supply, and about two-thirds of electricity is baseload. What is baseload? Baseload power sources are power stations which can economically generate the electrical power needed to satisfy this minimum demand. Baseload capacity is ideally coal or nuclear. This is the baseload or the power demand during summer in areas which can experience summer and winter. So there is really a peak load, a very big peak load, especially in summer. And below here, this is the base load that needs to be continuously supplied. And only two sources of electricity can continuously supply your base load. And this is your coal and nuclear. As you see here, this is the of California demand versus all nuclear, all wind, and all solar electricity production. So the black line here, this is your California demand for electricity. The the green one is for all nuclear, the blue is for all wind, and then the red is for your all solar electricity production. As you can see, if you compare your demand with your wind in blue, there is a very big fluctuation in the base load output or the energy output in your wind energy, because it's not always that you have a windy weather. So there might be times wherein your your wind energy cannot supply the base load. And comparing it with the solar, there's still a fluctuation because there is your daytime and then there is also your nighttime. Of course, in the nighttime, your base load will not be continuously supplied by your solar. And only your nuclear, the green line, can supply uh, your baseload demand continuously and reliability with great reliability. If no fossil fuels for electricity, how much production uh, can satisfy this demand? So there will be very hard time supplying with only your wind and then your solar energy. The next main driver is your economics and fuel cost. This is just a comparison of your uh, estimated levelized cost of new generation sources in 2016. Let's look at the capacity factor. So for your conventional coal, the capacity factor is around 85%. For advanced nuclear, you have 90%. For your solar, only 25%. And then for your geothermal, you have 92%. Compared to the other sources or to the other plant types, there is really a great capacity factor for your advanced nuclear. However, if we are going to compare the total system levelized cost, the cost throughout the years in maintaining and making or establishing a power plant, compared to your conventional coal, your advanced nuclear is actually higher at 113.9. But compare it with your solar and then your solar and just your solar. Your solar power plant is actually more expensive than your nuclear power plant. Um, your solar is around 210.7, but your advanced nuclear is just in the same level with uh your conventional coal, and then even in your geothermal and then your biomass. So there is really a big difference in terms of the capacity factor and then the total system levelized cost in your nuclear power plants. The advantages in terms of the economics for your nuclear power plant. Nuclear power plants are cheap to operate due to low fuel costs, as we've said earlier. If you have one nuclear pellet, this is more cheaper as compared to tons of coal or gallons of your petroleum. And also, it's stable and predictable generating costs compared to wind and solar. It has a long lifetime. You have supply security and then low external cost. So far, no credit applied. And this is the relative cost structure of power generation. For investment, um, if you're going to compare investment with nuclear, gas, and coal, you really need more investment when it comes to nuclear as compared to coal or your gas. It's because establishing a nuclear power plant will take at least 10 years. You need to pay a lot of consultants, and then the making of the plant itself or the constructing of the plant itself will take long years. So you really need a lot of investments, but in the long run, though you have a lot of investments in the beginning, you have a long lifetime for your power plants. And of course, it will be more cheaper to operate than compared to your coal and um, your gas. As you can see, the fuel is 15 to 20% only compared to the 35 to 40% operating cost in your coal. The next main driver that we're going to discuss is on the carbon emission cost. So you have principal concern of life cycle analysis for energy systems today, which is their likely contribution to global warming. It is of big concern nowadays, especially your coal power plants. That's why there are many rallies or many issues with coal power plants. A buildup of greenhouse gases, notably your carbon dioxide, appears to be causing a warming of the climate in many parts of the world, which will cause changes in weather patterns. Much of the greenhouse effect is due to carbon dioxide. And these are the bar graphs of your greenhouse gas emissions from electricity production, comparing your coal, gas, hydro, solar, wind, and nuclear. And as you can see, there is a high indirect um, indirect emission of greenhouse gases in your coal. Also, your direct emissions are high, direct emissions from burning. Also, in your gas, there's still um, a high direct emission. And comparing your coal and your gas with your nuclear energy is really clean. There's just a low um, emission of greenhouse gases for electricity production in your nuclear compared to your coal and then to your gas. So just around 21 and 9 indirect from the life cycle. And this one is just from not from the direct emission itself, but can be seen from the mining of your uranium and so on. So next here is your operational history and health effects. This is the cumulative reaction years of operation. So you have your reactor years of operation, and these are the accidents that had happened in the past years since the start of the operations of nuclear power plants. There were just three accidents that have caused large damages. One is the 3 Mile Island um, power plant accident, and then you have your Chernobyl, which is uh, which is one of the famous accidents in your nuclear power plants, and then you have your Fukushima, which is very recent, which we have all seen that happen in Japan. Comparing the accident statistics of energy production in coal, natural gas, hydro, and nuclear, you see that from 1970 to 1992, we actually have 6,400 immediate fatalities in coal, 1,200 immediate fatalities in natural gas, and 400 immediate fatalities in your hydro power plants. But we only have 31 fatalities in your nuclear power plants. And mostly in the coal, you have your workers of 342 normalized deaths per terawatt year of electricity. And then in your natural gas, it involves your workers and your public. For your hydro, it involves the public because as you can see, when your hydrothermal plants broke out, the water is released to the neighboring towns. So there will be more deaths from that as compared to the 8 workers in your nuclear power plants. So the basis for this one is per million megawatt electric operating for 1 year. And as you can see, nuclear is actually not really that dangerous compared to coal, natural, and hydro. But we're very much in fear of nuclear. Uh, and this is just because of the 3 accidents: your 3 Mile Island accident, your Chernobyl accident, and then your Fukushima accident. What we're referring here is the radiation, but we have already discussed in the previous lessons that radiation can actually be prevented if you use the right instruments and you follow the right protocols. So in summary, just from this comparison here, coal power plants actually uh, have more deaths compared to your nuclear power plants. So your coal is actually more dangerous. The other thing also is that your coal also creates more emissions of greenhouse gases. So why do you actually fear your nuclear power plants? Despite the main drivers of your nuclear energy that we have discussed in the previous sections, there are still many issues about nuclear energy that makes it hard to enter into the Philippine setting. So as you can see, we're just one of the countries which do not have a nuclear power reactor yet. And these are because of the following issues. First, you have your public acceptance. I think one of the reason or the main reason why your Bataan nuclear power plant was not filled up is because it happened during 1986, wherein in April 1986 you have your Chernobyl accident. And if you can remember, uh, Ferdinand Marcos was ousted from presidency because of people power in February of 1986. And by April 1986, it was now Cory Aquino who is in uh, in office, and her government decided not to fill up the Bataan nuclear power plant following the nuclear accident in your Chernobyl. So if you're going to ask many nuclear engineers or nuclear scientists, one of the reasons why the Bataan nuclear power plant was not filled up or was not commissioned was because of the Chernobyl accident. So there is a low public acceptance because the Filipinos fear that this may cause a lot of problems in the future. Also, another reason is that there was an issue with the structure of the Bataan nuclear power plant. The Filipinos fear that in one day this might create some accident, just like the Chernobyl incident. Another thing is after the Bataan nuclear power plants, there were no no other plans to construct another one here in our country. It's because of the high capital cost. One power plant can take up to 10 years to construct, and the shortest construction of your power plant was done in the United Arab Emirates. So they took them only 7 years. But remember that UAE is a rich country, so they have a lot of money to pay for consultants. They have a lot of money to speed up the construction process, which is what we lack here in the Philippines. Another issue is you have your nuclear waste, which is still an issue here or an issue now all around the world. Um, your nuclear waste is used to be how do you call this? It's used to be thrown into the oceans, no? But now there are other plans to construct waste facilities. But so far, most of the waste facilities are not yet in working. And um, also, you have your long timeline to start the first nuclear power plant. That's also another reason. And so far, those are the main issues why it takes so much time to commission or to construct a power plant, especially here in our country. So you have your public acceptance, your high capital costs, your nuclear waste, and a long timeline to start your first nuclear power plant.